Il faudrait mettre les camps.
Not necessary.
À la sortie, à droite.
No, you do that, right?
Pues no, iba a ir a ingeniero de la pero...
Cambio de similitud.
No fue por eso. Fue porque se levantó con... pasó la noche.
Y complicado lo de último momento cambiar el salón.
Porque está rápido a las 12 el curso general general. Se me preguntado si había, pero no, y después puso uno.
Yo creo que la parte se fue por lo primo. Sí. No por la jornada y de pronto valdría la pena ¿cómo se dice? Reservarlo, ¿no?
Pero está bueno.
Lo que pasa es que siempre está reservado, el horario siempre está reservado para el seminario general.
No, lo que está excepcional de todas maneras.
No es el horario normal.
Bueno.
Okay, so let's thank Julian Borre for his speech today. Please go ahead.
You thanked me before the speech.
No, sorry.
Okay, so, well, thank you, Nico and Marcela in particular, for allowing me to be there. It's a great time in the and to give this talk on different topics that the one we work on, which is some field of interest to me. I work on this with some old collaborators and students. And it's about scalar field dynamics, quantum field dynamics in the deSitter space. And as I'll explain, this has to be non-perturbative for physical reasons. So some words of motivations, I'll be quick. I just have one slide on that. So general motivations of studying quantum field theory in curved spacetimes obviously come from studying quantum fields in presence of gravitational fields, and obvious situations where this is of first interest are early universe cosmology, and in particular the theory of inflation, which is essentially based on quantum processes. So one motivation for the kind of question I will ask later is about understanding inflationary calculation beyond tree level in field theory, so going to loop, and as I'll explain later, this is a non-trivial question. Another important kind of application of quantum field theory in curved spacetime which comes to mind is the renowned black hole radiation, Hawking radiation from black holes. And the same story happens here. Hawking calculation is tree level in field theory, so you may wonder what happens when you include loops. And for this, you of course have to go to deeper in quantum field theory in curved spacetimes. These are the main motivations, most obvious ones. And others would be studying actual effects of gravity on quantum fields. And there has been in the literature some, for instance, proposal that typical phase transitions could be induced by curvature effects, so by the gravitational field. For instance, and other possibilities are, other motivations really come from the need to understand really what is quantum field theory away from Minkowski, and try to understand it as deep as we understand it in flat spacetime. Okay, that's all I'll say for motivations. And I'll jump directly in the topics. So the topics I will focus on is to study a very specific field theory. So the simplest one is a scalar field theory, and in a very specific closed space-time, which is the deSitter space. The motivation for the deSitter space is twofold. One is phenomenological. This is the typical space-time that you encounter in the inflationary cosmology. This describes accelerating expansion, exponentially accelerating expanding universe. And it has specific kinematics which lead to specific effects that I will describe later, which are really responsible for what inflation is good at, for the robust prediction of inflation. And another motivation for the deSitter space, more practical, I would say, is that this is a maximally symmetric space-time where you have a lot of symmetries which helps for the calculation, but still the basic difference with space-time which leads to very different physics and to the issues I will describe with loop calculations. So just in 2 lines about the deSitter space. So this is described by length relativistic invariant like this. So you have, in these coordinates, this is called cosmological time. This expansion parameter, the scale factor in cosmology, grows exponentially with some scale h, which is a constant. I will put this one to 1 starting from basically here. And that's co-moving coordinates. So you can see, for instance, this space-time can be represented, embedded in a 5-dimensional Minkowski space, as you may know, as a hyperboloid. But I will not need that. What I want to just point out in this space, for instance, is that, as I said, it is maximally symmetric, so it has as many symmetries as Minkowski. In particular, it has space translation invariance, which you see in this metric. This is clearly space translation invariance. And this is useful in particular when we want to compute loops, because loop calculations are a lot easier if you can go to Fourier space, as you probably know. And to have this luxury, you need space and time translation invariance. So at least we have space translation invariance. But we also have time translation invariance. We need to, in some sense, because, as I said, it's maximally symmetric. It has as many symmetry as Minkowski. And this you cannot see in these coordinates because the scale factor is done on time. However, you can shift to, so this is another way with another time called conformal time. So you can introduce a different time, and the metric would look like Minkowski in this conformal time and co-moving coordinates, time, an overall scale factor. Okay, that I will use this later. But you could go into other spatial coordinates called, in that case, it's simply this would be what people call co-moving coordinates, and this is just physical coordinate charges. It's just scale with the scale factor. In other situations, they have more technical names, these coordinates, but let's forget that. If you write this metric in these coordinates, you get this line element, where now you see that the element of the metric do not depend on time explicitly. Okay, so this tells you that there is time translation invariance that you can see in this coordinate system. However, you lose spatial translation invariance. So what is behind this is that you have a time translation generator. You have a generator of space translation. The difference with Minkowski is that these 2 guys do not commute. Okay, so that's it. That's the main difference. But this main difference means that the time and space direction will be tied together. You cannot diagonalize them at the same time. So technically it means you cannot go to Fourier space in all dimensions at once, so you have to deal with that. That's the technical part of what I will present. And physically this will lead to, as we see in some slide, to what's called the gravitational redshift. The fact that when you look at typical, co-moving wavelengths, say here, Okay, and you look at this as a function of time. If you translate this in a physical wavelength, you'll see that it's stretched by the expansion. So this also will lead to interesting physics in the sense that when we are used to separate between long wavelengths and small wavelengths and stuff like this, you immediately see that this kind of thinking has to be with care here, because what you call short wavelength today will be long wavelength tomorrow, essentially. Okay, so this is to prepare you to where are the issues. So scalar field in deSitter space, we have to start with the basics. So let's look at what is the action of a non-interacting scalar field in deSitter space. So there will be, I will work in a capital D dimension, which are one time and little d space. You have a invariant measure, then you have Klein-Gordon action with the box operator in the appropriate geometry. So I'll try to skip mainly the details throughout this talk. For those who are interested, well, this looks like this in terms of these co-moving coordinates and conformal time that I introduced before. Anyway, the equation of motion for this field is Klein-Gordon equation with this box operator, curved box operator, and this can be solved exactly. One way to do it is to go to Fourier space in space, so and do a Fourier decomposition as we do in standard field theory. But now I can do this Fourier space analysis only in spatial space. So you have a Fourier decomposition in d spatial dimension with Fourier waves, and then you can have what's called a mode function here. So you have a function for each mode, and you solve the Klein-Gordon equation for this function. In flat space, this would lead to the harmonic oscillator equation. So you would have a frequency E I omega t. Okay. Instead of that, here you're led to an equation which is of a Bessel type equation. You solve that with appropriate initial condition which describe the physical vacuum. Okay, I pass this detail, but the answer is that you get, instead of this plane wave, frequency wave E I omega t, you get an Hankel function. Okay, that's a particular function. And it is a function of momentum, co-moving momentum divided by the scale factor. And this particular combination is the physical momentum. So the length, physical length is scale factor times co-moving. So the invert of this typically is the physical momentum. So that's the physical momentum. So that's where we see that the space variable described by the co-moving momentum and time variable are tied together in the mode function, which typically describe the amplitude of the field at a given time. Okay, you can put a bit more to that, but basically what is interesting is to analyze the modulus of this function, which tells you about the amplitude of the quantum fluctuations in each mode in terms of the physical momentum. Okay, so I plot this here schematically. In fact, this would be a log-log plot. These guys as power laws. So what happens is that there is a typical scale in momentum. I call the momentum Z here. I forgot why, but well, okay, it's Z, momentum, physical momentum. There's a scale 1, which is H, the expansion of the Hubble factor. Above this scale, we are looking at momenta which are greater than H, so distances which are smaller than the curvature of space-time. And essentially, the curvature of space-time is a perturbation, so to say, and you get the Minkowski physics. And when you plug this function, you get the same power spectrum that you would get doing EI omega t. So that's the normalization of the harmonic oscillator. Below that scale, you are looking at distances, wavelengths, which are larger than the size of the horizon, of the curvature of space-time. And the field, if it's, here I took a massless field, okay, so I'll tell you why later. if the field is so basically the idea is that if the wavelength, the quantum wavelength of the field, so 1 over the mass, is larger than the size of the horizon, you have a regime where you have wavelength shorter than the quantum wavelengths, but still larger than the curvature of space-time, and these wavelengths do feel the gravitational field, the curvature of space-time fully, okay? And they experience a strong modification as compared to Minkowski. What we see is that the spectrum gets very much amplified, has a much steeper power law. In fact, this coefficient is given by the index of the Hankel function. The index of the Hankel function is essentially d over 2, okay, it will be 3 half in 3 plus 1 dimension, and there are corrections due to the mass of the field. Okay, so that's what happens. So at the end of the day, the picture is that you have a dramatic here gravitational amplification of quantum fluctuations at super horizon scales. Okay. That's precisely this power law. So if you take a massless field here, the power law in 3 dimensions, say, would be 1 over z to the cube, well, 3 half. And this precisely is this amplification of gravitational regime is precisely the power law you need so that the power spectrum that cosmologists consider for the cosmic microwave background is so-called scale invariant. So what they call power spectrum would be k cubed times this squared. So we get a scale invariant power spectrum, and this is what is observed. This is one of the very robust predictions of inflationary cosmology, and this is really based on this mechanism. Okay, so that's the good news of this picture. The bad news is that this power law is also precisely what you need. If you put now this power spectrum into correction to the 3-level calculation, you have loop diagrams. If you put this power law in loop diagrams, this is precisely what you need to make them infrared divergent. Okay, sorry. So that's the bad news. It tells you that the loop correction to your 3-level calculation is jeopardized. I mean, you cannot trust it. Maybe it's okay, but then you have to work more to understand why it's okay. And that's the whole point here. Okay, so finally to introduce this, I would be interested more specifically in the case of light fields. The reason being that if you have a field whose mass is larger than h, okay, you don't have long wavelength fluctuation. Okay, they are suppressed by the mass. They are not dynamical. Okay, so to make a picture, if I draw momentum, physical momentum scales on a line, I start from 0 to whatever. There's a typical scale 1 here, above which I essentially have Minkowski physics, below which I have potentially new phenomena. So if I place the mass of the field there, I will essentially have Minkowski physics to the mass and then nothing. The field is frozen. So if the mass is well below h, I have well, here the physics is again not decoupled, but I may have a large range of scales where there is no Minkowski space analog of what happens, and I showed an example before. So I consider this case, and I'll go to loop corrections. So this you can typically do. So let's take phi to the 4th scalar field theory, compute correction to the propagators. Here are typical diagrams that you meet immediately. So for instance, compute a correction to the mass, say, you'll see immediately that if you put this power law propagator that I showed before, this power law amplification, this will lead to infrared divergence of this type, which are regulated by the mass of the field, which go like 1 over the mass. Okay, so when you send the mass to 0, this blow up in this way. I call this, everything is infrared divergences, but I call this infrared divergences later in the sense of sending the mass to 0. Then there are other type of divergences in so-called non-local diagrams where the vertices are displaced, where you may, even in the presence of a small regulating mass, you still will encounter, you can compute this diagram, and you'll see that in the low momentum regime, this will go like a log of the momentum over the scale h. So if you look at pieces much smaller than h, what you will get is a large logarithm. Okay, this is not divergent per se, but still the logarithm can be large enough to invalidate your perturbation theory. And they are sometimes called secular divergence in the sense that they grow with time. Okay, remember that P is the physical momentum. Physical momentum goes with the scale factor, which is exponential in time. So this guy is in fact linear in time. So it tells you if you wait long enough, these diagrams are just growing. So this, all what I said before tells you that, well, your perturbation theory, at least in the regime of small mass, is not enough. You need to do something more, and you need to resum infrared divergences or just to have non-perturbative methods. Well, something else. Perturbation theory is dead to start with. So there are a lot of resummation or non-perturbative methods that we know in flat space. Actually, these problems are not really particular to curved spacetime. I mean, infrared divergences are all over the place as soon as you have massless fields, bosonic massless fields also in flat space. And there have been plenty of methods developed to resum these guys. Large logs are known in field theory. Renormalization group techniques are there to resum them. Secular divergences are known in flat space when if you take a typical system, shake it a little bit out of equilibrium and try to compute its relaxation towards equilibrium. Perturbation theory leads to secular contribution too. So also in this situation, in flat space, you have to resum. So this to say that many methods, because these problems are not new, they are applied here, but they are not new. Many methods have been developed over the years in field theory to deal with that. So the question, one question is to try to adapt this method to the curved spacetime situation, or to develop new techniques specific to this case and try to deal with this issue I mentioned before. So here's kind of a list of things which have been done for deSitter space physics. I will not list everything. I will just focus on the box here where I made my own contributions, and I will today describe some examples of methods which allow one to tackle this problem. One is large N techniques that I will describe. So others which I not mentioned in this talk are based on so-called Dyson-Schwinger equation, and I'll then spend some time describing a more recent and promising approach based on what's called the non-perturbative renormalization group, also called the functional renormalization group. You have a worldwide specialist here in Montevideo, so all the technical questions you can ask. So I will then focus on a particular model. I take a ON symmetric scalar field theory, so I have n fields, n copy of the fields, and ON symmetric phi to the 4 kind of interaction, so kinetic term, mass, and interaction. And at first I will describe large n, so I take n to infinity, and for this you have to rescale the coupling by n. This is called the Toft coupling sometimes. And if you do that, well, it's known that this theory has essentially first a limit, and the limit is very often analytically or at least exactly solvable. In this case, we'll see that we can do a lot of calculation, analytic calculation in that case. In terms of diagrams, so I'll first consider these, what I call infrared divergences, these kind of local diagrams, and in that case they appear in this diagram. So the large n limit, what it would tell you is that if you consider this diagram, it scales like n, because there's a loop here. Okay, and now if you add another loop, you add another factor of n, and thanks to rescaling the coupling by n, you have a 1 over n more, which kills this n. So this diagram also scales like n. And you can then, do an analysis and count, and you'll find at the end of the day that all the diagrams for the 2-point function which scale like n are these guys, the so-called cactus diagram. So it's essentially this guy, this also tadpole, iterated on itself up to infinity. Okay. This you can grasp, so this essentially tells you that you have just, the two legs are attached to one vertex, and this will lead to essentially a mass. Okay. So this leads to a mass resummation as is well known, right?
It's not one.
Yeah, one. You're right. It's yeah, okay. Yeah. It's the same order that
What are
the counting is this one. And this can be grasped all together into just one diagram where you put a fully resonant propagator in this limit. Okay, so I avoid the technicalities of deriving this equation, and I write this again. This is so again the action here I included in the mass just for you to not wonder what is mu. So mu means that I include in the mass a coupling, what's called a non-minimal coupling to the curvature. Here you can have Ricci scalar coupling to the field, and in the deSitter space this doesn't harm at all to send this because the curvature is constant. So having a mass, I mean this term or not, it doesn't change anything technically. So just forget this. The equation we have are an equation for the field, which looks like a Klein-Gordon with some recent mass, and an equation for the two-point function, which is needed because this recent mass is written here. So mu is the mass. You have the classical term, and there's a dressed guy coming from loops, which is nothing but this diagram in terms of the full propagator. So you also need an equation for this guy, and the equation in the large n limit is as simple as the same Klein-Gordon equation for the propagator. So you have to solve these two things together. Okay, this is the coupled equation. So it's interesting. Just for later, I will step out of the deSitter space for a while and go back to flat spacetime, Minkowski, and tell you what happens for this in this limit. This is an interesting.
What do you mean when you write leading order? It's the leading order of the one over.
Yeah. Okay. But I also said, don't look here. Please. Okay, just a reminder of what happened in this limit in flat spacetime. This is interesting for the rest. Let's consider a spacetime, ST spacetime translation invariant state, like the vacuum, finite temperature, an equilibrium state. In that case, the symmetries of the problem tell you that phi of x must be a constant, it cannot depend on x. It tells you also that the propagator cannot depend on all the variables, but just square difference, so one variable in fact. And in particular, the local propagator, which enters the definition of the mass here, gxx, cannot depend on x, okay, it's a one-point function, say. So the mass itself is constant. Okay, so you can then get what's called the gap equation for the mass. You have mass, the classical term, now it's m back because I don't have a curvature, classical term, plus this loop, which in Minkowski space is just 1 over k squared minus m squared, okay, that's the propagator. So you have this equation to solve. And the field equation, so that's the equation for the mass. Here the propagator is already solved because the equation for the propagator is very simple. It's k squared plus minus m squared, g is 1, right? So the equation for the propagator is solved. It enters, you see the mass which I have to solve is also the one here. So it's where it's non-perturbative. Okay, it's a self-consistent equation for the mass. This is where a resummation of diagrams appear. And then there's an equation for the field which, using these symmetries, look like this m squared phi equals 0, if you look here. Okay, the box is gone because phi is a constant, m is a constant, you have m squared phi is 0. That's the large n limit is just this, for the two-point function. Okay, so if this has two solutions, either phi equals 0, that's the symmetric phase, okay, or m squared equals 0, and phi is not 0, and that's the broken phase of this theory. And m squared being 0 is just telling you that you have Goldstone modes there. And in the large n limit, you have n minus 1 equals n equals infinity Goldstone modes. Okay. So that's, the field equation is as simple as that. And then the question is, m squared equals 0, if this phase exists, should be a solution of this equation. Okay, so one question is there a solution of this equation, which is m squared equals 0? And you can analyze this equation, this is kind of easy, and you find that this is not possible in d equal 2 or smaller, you'll find that there's no such solution. I'll come back to this later. And only for the larger than 2, so 3, 4, etc., can you have a broken phase. Okay, this is a particular case of the well-known Coleman-Wagner theorem, that there is no such broken phase in 2 dimensions. Okay. Why is it so? In 2 dimensions, you see you have d equal 2 upstairs, and now you ask that the mass be 0, so you have to put your finger here. You have d2k over k squared. The integral is infrared divergent, and these infrared divergence tell you that if you put m squared to 0, this is infinite, so you never have a solution with 0 here. Okay, period. That's it. So you conclude that m equals 0 is never a solution, m will never be 0, you don't have a broken phase, etc. That's d equal 2. So if you compute the effective potential, you can do that in the larger limit. In d equal 2, you'd find that, suppose you start with a classical potential which is such a shape. Now you compute the effective potential. What you'll find is that the effective potential is essentially, perturbatively corrected at large field. And then it would exponentially go to 0 here and have a minimum at phi equals 0. Although you started with, okay? So the picture is that the fluctuation in d equal 2 are strong enough, okay? So imagine you have this classical potential, and now you put your quantum fluctuation, which fluctuates like hell, and they don't see the 2 wells. So effectively, this guy see a potential which is symmetric, which has minimum in 0. Above d equal 2, you find that m squared equals 0 is a perfectly possible solution for this equation I showed before. And then what happens is that if you put m equals 0, this becomes an equation for phi, which tells you the actual magnetization, if you want to speak this language. Okay, then, well, the physics goes on. You can put some temperature on the system. You'll find that at finite temperature, the broken phase may be restored. There's a phase transition for d larger than 2, of course. You'll find that at large temperature, this kind of effects also lead to a thermal mass, okay, which at large temperature can be computed, and the thermal mass goes like temperature. So the only scale is temperature, so m squared would be temperature squared, and it goes like the coupling. Okay, this is typical thing which happens in flat space. So back to deSitter, just to see. Again, I will consider a state with the maximal symmetries of the space-time, so a fully deSitter invariant state, which is an assumption. If I do that, again, my field cannot depend on x because it is maximally symmetric, so for the very same reason it must be a constant. The 2-point function depends only on one variable, which is the deSitter invariant distance between the 2 points. And again, when x is x prime, this is going to be a constant. Okay, so the mass is a constant, so I can write an equation for the propagator. My equation for the propagator boils down to the Klein-Gordon equation with a constant mass, unknown, but still I can solve it in terms of this Hankel function I showed you before. So what takes the place of the propagator will be this Hankel function, and I have a gap equation. Same story. M squared, classical guy, the field contribution to the classical mass, and then the loop. In terms of a index nu, which involves the mass I'm looking for. So the same self-consistent structure, but with a different guy here. Now, you can immediately see what happens. In the zero space, I told you that now the question is, can there be a m equals 0 solution? And I've told you before that if you look at the low momentum behavior of this propagator, it goes like enhanced power law because of this gravitational effect. And if I put mass to 0, this will be z to the minus d in any dimension. So you see in flat space, the infrared problems appear because your propagator is 1 over k squared, so they appear only in d equal 2. If you put more dimension upstairs, no infrared problem. In the zero space, because of this gravitational amplification, the propagator goes as 1 over z to the dimension, so you can put more dimension upstairs if you want. The propagator follows you, right? And you get an infrared divergence here, right? You get dz over zd. Okay, so you really need the mass to regulate this integral, and if you try to find a solution with mass 0, you don't. As simple as that. Okay, so you find that again the Largen non-perturbative resummation generates a non-trivial mass. It cannot be 0, so if you start with a 0 mass, a mass will be generated by the theory, and this tells you that the theory cures itself somehow. It generates its own mass, which then regulates the loop diagram, which then has a solution. Okay, so this is what I said. You can see that having a solution to the gap equation requires that this nu being strictly smaller than or equal to, or d over 2, which means that the mass must be strictly positive. No other solution. So the immediate conclusion of that is that these infrared effects in gravitational amplification prevent, so this large quantum fluctuation in any dimension due to gravitational amplification prevent the possibility of a broken phase, just as in flat two-dimensional flat space. Okay, you can go on and solve the gap equation. So an interesting check is to see what happens for large mass in units of the space-time curvature. And well, you work your way and you find that you recover what you would get in Minkowski, which is what you expect, but that's a nice check. And then you can try to solve the equation when, in the interesting case, where the mass is small compared to h. In that case, you can, expand, like perturb, and find that the generated mass will be the classical mass plus a loop, and the loop, as I said before, diverges in 1 over m squared. Okay, so you're left with an equation for m squared that you see is quadratic, so that's something I know how to solve. And here is typical solution. You analyze all that. First of all, you find that if you start with a 0 mass, the so-called minimally massless, minimally coupled field that cosmologists like, massless means you put m equals 0, minimally coupled means you put disk side to 0, so it's the one which appears typically in inflationary theory. Well, you see that any loop diagram that I showed before, all these tadpoles over tadpoles, all of them are just infinite. So you have infinite plus infinite plus infinite. Nonsense. However, if you approach this with a non-perturbative approach like the Largen limit, you find that in fact the theory, by resumming infinitely many guys, generates a mass which cures the infrared the infrared divergences. And you can compute this mass in this case, and you find something interesting. So the mass goes as h squared, which tells you that it is of gravitational origin. So this is a bit like when you put temperature. But now here, at the difference of the finite temperature case, the scaling coupling is not lambda, but root lambda, which is also a sign of the infrared origin of this problem, which typically lead to non-analytic behavior in the coupling. So it's you do not have a well-defined expansion in lambda, but the expansion parameter is actually root lambda. Okay, that's one interesting effect that you have here, and you can go on and compute the potential, and you find that as in the picture I showed before. So you get an analytic expression for the potential. That's a nice calculation one can do, and you find that you can even start with a classical potential with classical symmetry breaking. The classical level, you find indeed that non-zero mass at zero field is generated, so the curvature becomes positive, and the effective potential really gets a nice shape with minimum in 0, and it's even the lifting of the symmetry breaking is even stronger than in d equal to field theory in flat space, where the potential would be exponentially flat. Not exactly flat, but exponentially small. Here it's just a quadratic potential. It really is a strong effect. So the physics is not as I also explain later, is more of d lower than 2 than d equal to. It's the infrared effects are even stronger than the d equal to physics. Okay, that's an example of a dramatic effect of this amplification and of this non-perturbative modification of the theory due to this gravitational physics.
But does it mean that it destroys inflation?
No. No, because, all these calculations assume that the mass, even the generated mass, is small. So you need to keep this mass small. And furthermore, this is a toy model where my phi to the 4 potential is not the one responsible for inflation. Okay, so I should have said that. Here I play a game where I fix the geometry, and this would be inflation physics. And I put a test field on this, just to see what happens. So this would be what people call a spectator field during inflation, so it has an implication for this kind of field, but if you want to look at the implication for the inflaton itself, you'd have to apply this to the inflaton potential, which is not phi to the 4,
okay,
which has derivative coupling and gauge symmetries and stuff like this, so it's a whole different story. But this is, this illustrates, it also has infrared problems, much more tricky, but this phi to the 4 illustrates the problems and possible solutions, etc. Okay, that's the point here. How much time do I have left?
15 minutes.
15 minutes. So I will skip this part, which would have been how to. Another example in the large N limit where you can resum these large logs I mentioned before. Okay, but this is more technical, and the bottom line is that again, the large N limit allows you to resum, solve, and have interesting consequences for some observables that people are looking in inflation, typically non-Gaussianities. You find just the bottom line of this is to say that taking into account these effects in the large N limit and computing, say, the 4-point function of the theory, what you find in this limit that I showed is that the loop corrections, so you have a 4-point function which would be this, and now you need large N tells you that these guys, all these guys contribute the same here. So you have to resum them. Each finite loop order would have large logs, and the sum of them don't. And these logs resum to power laws, a bit like in statistical field theory, the generation of a Manu-Manus dimension. So the bottom line is that. But then you can plug this resum solution into what I showed here, the 4-point function, and compute what's called the non-Gaussianity in inflation. So what measure the non-Gaussian character of the state. And you find that these loop effects, because of this infrared, this gravitational enhancement, the loop contributions are the same order as the tree-level one. No suppression by even root lambda, none, just the same order. And they have a much different structure in terms of momenta. Okay, but I skip that. I would like to use the remaining time to discuss another approach, which I think is very interesting and powerful to deal with these issues, and perhaps also for other theories, which is the non-perturbative renormalization group. So it's based on the old Wilson ideas of the Wilson renormalization group. So in a nutshell, the method here is to say you have a. So this has been very much used in statistical physics, but in many areas where one has to deal with infrared problems. So the basic idea is to regulate the infrared part of the theory by modifying the action, adding a quadratic term in the field which plays the role of a big mass. Okay, so you add a momentum-dependent mass, and in terms of momentum, what you do is to add essentially nothing to the large momenta, so you leave these guys alone. And for the low momenta, the one which bother you, you just give them a huge mass. So you kill their fluctuations. You say, shut up. Okay, that's it. And then you ask yourself when you do that, so essentially there will be a scale where you ask people to shut up, you put a large mass, and then you will essentially use RG ideas to lower, Wilson RG ideas to lower the scale to 0, which means you will integrate out longer and longer wavelengths step by step, and this allows you to control, to get the final theory by this limiting procedure, and to, in fact, at each step the theory is regulated, so at each step it's finite, and you get to the final theory this way. Okay. So basically what you can do when you do that, you can go to the effective action, a slight modification of it, but the so-called effective action, the one which generates the one particular reducible function. And for this you can write an exact equation, which is an equation for an exact equation for the dependence in this scale. Okay, it's so-called, well, it's now named the Wetrich equation. And it involves, well, it's written here, it's a functional differential equation, it's a complicated guy. It involves the action, the full action here, functional. Here you have also a functional, which is the 2-point function in presence of the regulator, inverse. So this would be the propagator of this theory, of the regulated theory, the full thing. And here appears the derivative of the mass function, which basically, the mass function, just to make a picture, is basically flat here, basically flat there. So when you do the difference you compare two theories with regulators which differ one from another in some area around K. So basically you are this equation, take a slice in momentum, and you'd go from, in the case I'm interested in, a large momentum scale, down to h, and down to 0. That's what I want to do. So there are various ways to approach this equation, which is exact. One cannot solve it like this. So one way is to do ansatz. You guess the form of the solution, you plug it in the equation, and you hope it works. And one very powerful and simple ansatz is to do what's called a derivative expansion. If you are interested in long wavelength physics, typically what you say is that I expand in powers of long wavelengths, so it's a gradient expansion, say. So you start with a function of the field which has no derivative, and then you add derivatives more and more. You cannot start with just the potential, because this would not be a theory to start with. You need something which resembles the basic action to just start with, and then build on it. So the least thing you can do is the classical, the initial gradient term, no renormalization there, and a fully dressed potential that you have to solve for. Okay, you take this ansatz, throw it in the equation, take your preferred regular mass function. Okay, of course, an approximation will depend on your choice for the mass function. But, okay, then you have to work out the dependence on the mass function, etc. I put this aside, and you get, instead of the equation for gamma, you now get an equation for the potential, which in this case you can go on, write, etc. And the result is here. So we have an equation for the potential which looks like this. There's a constant given there with some numbers, forget it. K dependence, dimensions, K dependence. Here is the second derivative of the potential, so this would be the curvature of the potential, so local curvature. And then there's this big function B here. Don't look too much at it. The point is that here you have some coefficients, and what appears below, is simply the expression of the presence here of the propagator. Again, this propagator is governed by Hankel functions, so it's no surprise to see these Hankel functions appearing here at the scale K. So Hankel function, derivative, etc., etc. Typical. Now we have, so in this ansatz boils down to this exact equation for the potential. That's the flow equation of the potential. It tells us start with lambda phi to the 4, and then integrate out more and more UV infrared fluctuations, how is renormalized? How is the potential renormalized? So that's the equation. We can solve it. Before we can analyze the various regime. So there's a regime. What we will do is to start with a high scale and go below, go down to 0. Okay. So at large scale, you can well take the large k limit of the encode function. You're back to the exponentials, and you get essentially what you would get if you do the same in Minkowski space. So I guess you don't recognize this, but you can check that if you do the very same thing with the very same regulator in Minkowski space, the flow equation you get is this one. So that's a check somehow. So you'll flow. So it tells you that as long as your mass functions, your regulator is larger than the scale of gravitational effects. You don't have gravitational effects. Okay, that's the standard flat space-time flow. And the physics is well known here. You will have broken phase, etc. Depending on the dimension, etc. Then you cross the scale and you analyze the infrared flow function. And again, you see what happens here. I can point to you. The k dependence is essentially here, and this has a power law dependence, as I said before, 1 over k power d, right? And here there is a k power d. So this 1 k power d is going to be killed by this 1 over k power d. So at the end of the day, you can analyze this, you'll find that the power here is eaten just by the large fluctuations. Okay, the 1 over k here tells you that the fluctuation you're integrating out are just huge, and they just eat this power. So eventually, the flow equation you get in the infrared, it looks like this. So you see d as this, well, d is in the coefficient, but this is, you can absorb it away. The d dependence of the flow function has disappeared.
It's like d equals 0.
Exactly. So for specialists, you immediately recognize that if you do another problem, suppose you do a flat space, Euclidean flat space, in capital D dimensions, okay, and write the very same ansatz local potential approximation, write the flow equation, you get this equation with 2 plus D or 1 plus D, I forgot. 2 plus D, I think, here instead of 2. So this is the same flow equation as you would get with a zero-dimensional space, formally. Okay? So this phenomenon I just described leads to an effective dimensional reduction of the flow. You start from the flow in, well, whatever dimension you start with, and you end up, every theory in any dimension end up with this flow, which is the same flow that a theory with 0 dimensions, say, would have. Yeah.
Is the root missing?
Yeah. No, well, there's a trick.
So
this is what you get in D dimension if you do the same regulator I used. But this regulator I used is not completely Minkowski invariant. So there's a tricky thing here. But with this regulator, this is what you get. This happens for reasons. I mean, it's like this. This happens to have the same form as what you would do with in Euclidean space with a completely symmetric regulator function. So it's not that this is the 0 dimension of this.
Okay.
Okay, but it's just formally it's the same equation as I said. You take a capital D dimension Euclidean space. You take a OD invariant regulator, and you would get this in D equals 0.
Your analogy is regulator dependent.
This I don't know. The phenomenon of dimensional reduction, I think no. But whether this boils down to
the precise form.
Yeah, this form is not the one I would get with this regulator, etc. So I'm not saying there's a reason. I'm just saying it happens to be this. Once this is observed, you know that the infrared physics will be just described by the solution to this flow. This is what it meant for. But you don't. I mean, once you remark that this is a like low-dimensional statistical physics system, you don't have to think too much. I mean, everything is known for these systems. In particular, it's known that below d equal 2, there is no broken phase. So you immediately conclude that here, there will be no broken phase possible, which goes in the same sense, the same conclusion I drew before, but this was drawn from the large n limit, so maybe it was large n kind of peculiarity, etc. Here, this is very general and very simple. The way it happens is very simple. Okay, plus the nice thing here is that because it is a zero-dimensional theory, what is a zero-dimensional field theory? It is the path integral is an integral. Okay, so you can solve this with an integral, which is you take your path integral in one dimension, and that's it. Okay, so you can show that if you take now some potential, you do the Legendre transform to get the effective action, you get a mass function, which is just a mass. You write the Wetterich equation for this theory. It is this, the same. Okay, so you show that you can replace this by an integral thing, and now the only thing is your initial condition, and the point is that the initial condition is the guy you have to put here. So if I want to start phi to the 4 and look at the flow, I put phi to the 4 here, period. Okay, so.
But the initial condition should not be the resulting of the flow from your true initial condition up to the horizon.
So yeah, there are two ways of seeing this. Either you say, well, I imagine that the theory at scale h is phi to the 4, and then I look at the remaining flow. Or you can say, well, I start with lambda phi to the 4 much above h, and then I look at the complete flow. Mm-hmm. Either way. Okay, I'll skip that. You can do the same on Euclidean deSitter, so which is a sphere. I said that, so I can skip it. Just now I show you what happens. So for instance, this is a plot of, as a function of this scale k, this quantity is the minimum of the potential. So I start with a potential which has symmetry breaking shape. There's the minimum of the potential. And this potential will be renormalized, so it will change shape as I lower k. And the minimum of the potential will move. Okay. So the various curves show different. So this is large. This is h. This is 1, right? This is Minkowski physics, and this is gravitational deSitter effects. When we start here, we start with always the same condition. We made d equal 1, so 1 plus 1, 2 plus 1, 3 plus 1, just to illustrate. And the dotted curves, the dashed curves.
This is n equal 1.
This is n equal infinity now. So we solve the flow in the n equal infinity limit where you have analytical formula, but you could do it with a bit less simple formula for any n. Including n equal 1, but then the picture is not like that. I'll show a picture for n equal 1 in a minute.
No, sorry, but I don't get. In d equal 1, you shouldn't get.
In d equal 1 plus 1. No, this is small d. So space time is 2.
Yeah, so you shouldn't have a broken phase.
Yeah, so if you wait long enough.
Ah, okay. It's very slow.
Yeah, it's log.
It's log.
So in d equal 2 or 3 or 4, so the dashed line are the one you would get in Minkowski. So if I just turn out the gravity, and the other one are the one with gravity. So what you see is that the flow are just the same. Minkowski are not above h as expected, and below h very very quickly you see some difference, and that's because you have this dimensional reduction phenomenon appearing in one case and not in the other. In particular, one can check that the beta function of all dimension boils down to the same in deSitter, where they keep being different in Minkowski. And what happens is that in d equal 3, you start deep enough in the broken phase, you would end up in the broken phase. This is flat forever, and you end up with a non-vanishing minimum of the potential at 0 scale. Same in d equal 2. In d equal of 1, so 1 plus 1, you would have no broken phase. This is the Merlin-Wagner theorem, but this is a very, very, very slow flow. So if you continue this, you may see a little slope here. It will go to 0, and it will reach 0 at k equals 0. That's two-dimensional physics. The deSitter physics is zero-dimensional. So you see that the departure is, as soon as it starts, it gets there, and you find that rho reaches 0 very quick, and before k equals 0. So then you restore the symmetry during the flow at some scale, and then you have a symmetric theory, and the rest is just generating a new functional. So it starts like this. Well, I show pictures. Okay, these are pictures of the mass of the excitations. So the mass here, they are in the when the flow is in the broken phase, say. Okay, before the symmetry gets restored, you have two masses, the longitudinal guy and the transverse guy. Transverse one is 0. This is Goldstone modes. The longitudinal guy, it does what it does. And here is what they would do in Minkov flat space. So in the broken phase, the Goldstones stay Goldstone and the longitudinal stay massive, and they are different because you end up in the broken phase for these initial conditions. In the deSitter, as soon as you cross this scale, you see these effects coming down, so coming up, so the symmetry gets restored, and here you have a restored potential, so it's initially flat, the mass is 0, and then it becomes even more peaked. So the mass of in all direction, because now it's degenerate, is generated, and you have symmetry restoration followed by mass generation, which you can compute exactly the value of the mass because it's just given by an integral that I showed you before with lambda phi to the 4th. You get the result. The same flow for the coupling, but and that's the same case where you would restore the symmetry right at the scale k. So the case we call the critical. So this would be the critical case in flat space. This would be initial conditions, which are called critical in the sense that you end up right at the transition. Okay. In that case, because of the deSitter effect, well, you restore the symmetry and then you generate the mass. So there's no criticality. N equals 1 has a different way of restoring this symmetry because for n is 2 and bigger, this is completely driven by the presence of Goldstone modes. And as a byproduct, you can essentially forget of the massive mode and the flow of the Goldstone mode, I can show you here. Yeah. So the Goldstone has 0 mass. So the flow is, you see, you put your hand here, the flow is this. So it's very simple to solve. I'm sketchy here, but that's essentially what happens. For n equal 1, you need to solve the full flow functional equation. And this is an example. You start with this potential, you flow a bit, you get this potential which flattens a bit, and you flow again, and you restore the symmetry. And just an interesting comment for specialists. Here, if you would do a field expansion, you'd find you never see that. You really need the full functional. If you truncate up to say 5.4, 5.6, you find a spurious phenomenon that you do have a critical transition, which is completely not there if you solve the full flow equation. Okay, I'm done. I try to convey the fact that if you put just the simplest field theory on the deSitter space with a small enough mass, like phi to the 4, well, this is already very interesting and non-trivial, and it has rich dynamics, which have which you need to which is interesting per se, and also maybe important for actual applications. Okay, I think the rest I said. You need non-perturbative techniques. I presented a few of them, and there are non-trivial phenomena such as dynamical mass generation, symmetry restorations, etc., etc. Okay, thank you.
Is there any questions? Please.
Dynamical gravitational field.
The different fluctuations of the scalar field.
So I can tell you because we did that. So recently with a doctoral PhD student, we studied how these what happens if we now allow these fluctuations to back react on the geometry. So we did that by modeling this, basically saying that now we will on the top of solving so we did that in the NPRG kind of framework where we can nicely formulate this semi-classical problem now. So you have a quantum field and a classical geometry, and what you do is to solve at each step the flow equation in a given geometry, and then together with that you make this as a source term in the Einstein equation for the geometry, the classical Einstein equation. There's one way to do that properly. And then you solve for the potential and the running of H. Okay, so now I have to simplify the problem. I cannot pull full fluctuating gravity because this is way too complex. This is quantum gravity, and I don't know how to do that. But what I did here is to assume that you stay with the deSitter symmetry, so the gravity is just described by a scalar, which is the scale, h. So you have an RG equation for h, essentially, and then you look at what happens. And that's this is because of one of the original motivation I showed there, which I did not comment, which is understanding what is a quantum field theory in curved spacetime. For instance, there are a lot of statements or supposition that just putting this scalar field theory on deSitter would destabilize deSitter by this phenomenon. If you allow the fluctuation to back react, because they are so much amplified, the idea is that this amplification is the field taking energy from the gravitational field. Okay, so eventually the gravitational field should lose energy to the quantum field and decay. So your deSitter curvature should diminish with time. That's roughly the picture. Okay, but this is, I mean, a lot of these arguments sometimes are based on studying the perturbation theory and seeing that it grows. Okay, so you imagine that there's an instability. Here I have an example where I can control things and I see where this growth eventually saturates. So you can ask whether this would whether the growth will destabilize deSitter and eventually this makes an avalanche and deSitter is destroyed, or that whether it's not enough and this saturation of the growth will then saturate, just renormalize your scale, and that's it. This is what we found, this second thing. Interestingly enough, what I saw before is that in the situation where you have a broken phase, not restored yet, you have gallstones, and these guys are massless, and they have, because they are massless, as I said, massless will have huge fluctuation. So I thought this guy will have the main effect on running the running of the curvature, right? And so what we could show is that at this level, so local potential approximation, is that instead you can show that the gallstone has strictly no effect on the running of the curvature. Nothing. So as long as you are with gallstone, the flow of the curvature is zero, and it's the longitudinal guy which drives the flow. But the longitudinal guy, because symmetry gets restored very, very quick, and there is dynamical mass generation, you do have a flow, but as soon as a mass is generated, the flow stops.
Is this a feature of the LPA, or?
Sorry?
Is this a feature of the LPA? Do you have any idea?
I don't know. This is what happens in the LPA, this I can say. Whether it is restricted to the LPA, I don't know. I would not think so. Because I think this phenomenon of mass generation is pretty robust. It's essentially due to this dimensional reduction, and letting what we saw is that letting the scale at least fluctuate or get renormalized is not enough to kill this phenomenon of dimensional reduction. So mass is generated, and when mass is generated, the flow stops. Okay, but again, it's not full gravity, so it doesn't contradict or answer the question whether the deSitter is stable or not against quantum fluctuation. But well, it's the best we could do in a controlled way. Yeah, sorry for the long answer.
So at first you were giving us some motivation about inflationary dynamics and talking about the scaling variant spectrum, power spectrum, right? So how is this modified with loop corrections that you?
So one way. So again, what I can say precisely is the power spectrum of the spectator field is modified by these effects, because applying this to really the power spectrum of the primordial fluctuations, which is one mode of the gravitational field, would require to use the proper interactions, which is not lambda phi to the 4. But still, what I can do here is to compute the power spectrum of say curvaton models in inflation, where you have the inflaton which drives the inflation, and you have other fields which interact with it. So here I can compute that. And the modification is essentially described, well, I don't know. No, I don't have the slides. So what happens is that all these resummations, which produce large logs, when you resum them, produce kind of an anomalous dimension. So the power law I showed before, 1 over ZD, gets modified by something which depends on the interaction, just like an anomalous dimension. The point is that this modification of the power law would then give a change in the power spectrum being either completely flat or a bit tilted. Okay, and unfortunately I don't have the expression there, but well.
But it is modified in a noticeable way.
Noticeable, I don't know. It's still. I mean, this whole the calculation I can do here rely on either. I mean, these anomalous dimensions are small. Okay, they are controlled by 1 over n or by coupling or something like that. But they are there. I mean, but I don't know if, again, because it's not really the power spectrum you measure in inflation. I don't know whether these other possible fields are accessible by measurements or something like that. This I don't know.
In the case of the large n calculation, it's clear that you need to 5 to the 4, but in the LPA case, you could put another potential. Why to?
Yeah, you're right. You can even put fermions but
but keeping scalar theories, you could put another potential with but because you say I cannot say anything about inflaton, but you could put that.
Because in the case of inflaton, you have symmetries which you immediately gauge symmetries.
Okay.
Which you immediately break with this, and
Okay.
I don't know how to control that. But well, apart from that, you're right. You can put any potential you want in this picture.
Okay, but not okay.
Well, let's thank you again.
Well,
Thanks.